So if it's okay with you, I think we kind of have a combination of, so go ahead and ignore my yapping if you want to. Otherwise, I'm gonna kind of work it up here, ask some pointed questions. What I usually do is something like this, and I haven't worked these, so this is kind of scary. But how many milliliters? So I'm gonna put milliliters over there. Bless you.
Thank you.
Of a solution that is 0.245 molar. Sorry. I'm going to use this 0.921 moles as my first thing. 0.921 moles of NaCl. So for those of you who watch the videos, how do I go from moles to volume here, to liters? Using molarity. Great. So I usually, if we unpack 0.245 big M, what does that mean? 0.45, I said 0.25, 0.45 big M. It means 0.45 moles of, in this case, NaCl per 1 liter. Yep. Just like the Autumn gave us that cute 2 moles per liter. 245. Cool. So I'm going to use that as a conversion factor. 0.245 moles NaCl over 1 liter. So I'm going to use that to get from moles to liters. And then how am I going to get from liters to milliliters? Yep. 1,000 milliliters is equal to 1 liter. So my first term is going to be the 0.921 moles NaCl over 1. So 0.921 moles NaCl over 1. Awesome. Now how can I use molarity so that my moles cancel? Yep, the reciprocal or the flip. Exactly. I'm going to put 0.45 moles NaCl in the bottom and 1 liter on the top. And then how am I going to get from liters to milliliters? Yep, I'll put 1,000 milliliters over 1 liter. Perfect. And then how many sig figs do I need to round the answer to?
2.
Just 2. I'm liking it. Well, let's see if we get the same answer here. I love the sound of those calculators warming up. Wow, so you guys told me 2 sig figs? I'm going to have to use scientific notation. Yep, only 2 sig figs because I have 2 here, I have 3 here. Because it seems like it's been a while since we've done this, but I think that my Thanksgiving break just really did it to my brain. So what your calculator displayed, was it 2046666 repeating?
Mm-hmm.
Okay, so 2 sig figs, I'm going to have to what? Truncate it right here between the 0 and the 4, right? Oh, go back. Between the 0 and the 4. So I'm going to have to go, to me, I'm going to have to go 2.0 times what? 10 to the 3rd. Does that sound right? To show 2 sig figs. And then what would the units be? Yep, milliliters, because moles canceled, liters canceled, milliliters. Yep, very good. Would you go back? Any questions about that?
Does it have to be like milliliters of solution with it?
That's a good question. I usually put milliliters solution like SOL apostrophe N, but just milliliters would be fine too in this case. Okay, let's do another one. Dun, dun, dun. That was moles to volume. This is volume to moles. In this week's lab, the copper lab, here in a minute, you're going to do several of these calculations. Sometimes it's hard, and I read a question several times before I'm like, oh, that's what they want. So it gives the volume of a solution, it gives the molarity of the solution, and it says how many moles. Well, I know then over here on my right is question mark moles. And I'm probably going to use molarity as a conversion factor again. I'm going to start with my 1.76 liters, or liters of solution, yep. So how would I unpack 1.33 big M? Yep, moles over liters. So that means 1.33 moles. I'm going to be specific of NaNO3 per 1 liter. I'll go ahead and do my of solution. 1 liter SOL apostrophe N per solution. That's what molarity means. All right, so what's my first term going to be? Yep, 1.76. I'll even go 1.76 liters SOLN, liters of solution. Cool. So how can we use molarity to get liters to cancel? Use it just like that, 1.33 moles of the NaNO3 over 1 liter solution. Perfect. Liters of solution cancel. And by my account, we're done. We have moles. Okay, so how are we going to round it?
3.
I'm liking 3, yep. 3. I get 2.34. Does that sound right? Good. Units would be moles. Yep, moles or moles of NaNO3. It looks so easy when somebody else does it. Okay. Any questions? Okay. Preparing a solution. So these really lend themselves to pictures. So I'm going to go ahead and draw a picture. It says I'm dissolving a certain mass of NH4Cl. So I'm going to go ahead and draw my little beaker, do an arrow, and I'm going to put 7.23 grams of NH4Cl, ammonium chloride, right? And it says that my final solution volume is 500 milliliters, but don't forget, is this decimal important here? Yeah. So I'm going to say, and it probably wasn't in a beaker, it probably was in a volumetric flask, but my solution volume is 500 with 3 sig figs milliliters solution. And here the question is, what is the molarity? So question mark M. Well, let's just go ahead and say, what does molarity mean? Moles over liters, yep. So in this case, molarity means moles of NH4Cl over 1 liter of solution. Perfect. So this is one of those where you kind of step back and you're like, that's my target, moles of NH4Cl over liters of solution. If I look over here on the left, I have grams over milliliters. Okay, so actually to work this problem, I'm going to go ahead and just go with the grams over milliliters and then kind of make things work out. How can I get from grams to moles? Molar mass, yep. So actually, let's go ahead and knock that out. I'm going to do mm of NH4Cl. So you guys are good. Keep up the good work. Always show me your calculations here. So I got 14.01 plus 4 times 1.008. Some of these you probably have memorized too. Plus, is it 35.45? Okay, very good. We add all that together, just like cooking. Did you get 53.49? Okay. 53.49, and what would the units be? Grams per mole, G/mol. Kind of running out of room there. Remember, and I'm going to fluff this out, I'm going to unpack this. Remember what that means is 53.49 grams of NH4Cl for 1 mole of NH4Cl. That's kind of what that means. All right, I'm going to go for it. Like I told you, the way I work this is I just put that mass over that volume. So here I go. 7.23 grams of NH4Cl over 500, 3 sig figs, decimal, 500 decimal milliliters of solution. How can I use my molar mass to make grams cancel? Yep, flip it. So that up there, the 53.49 grams per mole, I'm going to put down here 1 mole. I'll go ahead and be explicit. 1 mole of NH4Cl over 53.49 grams of NH4Cl. Cool. So I know some of you are like me, you don't like to cross out the units that cancel because it looks so messy. So if we cross out the grams, now we have moles per milliliter, but we need moles per liter. So what's a third term I can knock on there to get units of milliliters to cancel in the denominator and get units of liters in the denominator? That's what you were going to say. Yep, 1,000 milliliters. And this is sometimes where I'll go ahead and say 1,000 milliliters solution. You wouldn't have to. I get kind of sloppy like that. Oops. 1,000 milliliters solution over 1 liter solution. So now unit-wise, that did it. That made my milliliters cancel. So now my grams have canceled, my milliliters cancel. I have units of moles per liter, which is perfect. So how many sig figs do I want around this table? 3. All right, I got 7.23. Gotcha. 500. It's like an accountant. You told me 3 sig figs, so is it 0.270? Okay. And units would be, right, units would be moles over liters. Or sometimes you can just go put 0.270 big M and then put the thing that it's the solute, NH4Cl. Well, I'm kind of messy up there. Okay. Alternatively, you probably figured this, what you could do is you could take that mass, knock it out to moles, and then divide those moles by that volume. You could take that mass, knock it out to moles, convert that volume to liters, and then take moles over liters. Definitely different ways to work this, whatever makes sense for you. And then I threw one of these in here. This is actually kind of going back to week 12. They're so fun. Let's do one more. So on your unit exam, you'll see a simple stoichiometric calculation. Now, there's no calculation here. And so we get to make it up. Let's say, let's say this is a chemical reaction for NaN3 produces Na and N2. Let's say we get 12.63 grams of N2 are produced. Stoichiometric calculations are simply, you know the mass of something and you're supposed to find the mass of something else. I'm going to put my question mark under my NaN3. So In other words, like if this was on the test, it would say, it would give you this reaction, and it would say how much NaN3 is required to produce 12.63 grams of N2. That's what the problem would say. I just put it up there, those things. So what we did before is we know that we can use this mass and the molar mass of N2 to get to moles of N2. So I'm going to say, I'll put G for grams of N2. Maybe I should put mole. I think I did mass before. I'll put mass. Mass of N2 instead of G. Mass of N2 to moles of N2. How do we do that? How do we get from mass or grams to moles? Molar mass. When in doubt, do you use the molar mass? Yep. Then we're going to go from moles of N2 to the moles of the NaN3. And how do we do that? Not the molar mass. Good.
Stoichiometric
Yep.
ratio.
Stoichiometric ratio. Yep. This is the stoic ratio right here. Yep. That's the stoic psych ratio. Yep. And then we're trying to get to, I should have put question mark, I'll put a little G, question mark, grams over there. So how are we going to get from moles of NaN3 to grams of NaN3? Molar mass, yep. Yep. So I told you my favorite way to work this problem is to kind of, you can actually work three separate problems, if you want to, but I like to string them up. I like to knock out my molar masses kind of in the margin. Molar mass is in the margin. So the molar mass of N2, I'm liking 2 times 14.01, 28.02 grams per mole. And then, oops, we need the molar mass of the NaN3, and that looks like 22.99 plus 3 times 14.01. I'm liking 65.02. And units would be grams per mole for that compound. So what's my first term going to be? Yep, 12.63 grams N2 over 1. Yep. 12.63 grams N2 over 1. Now where do I go with it? I'm going to use the molar mass. I'm going to use
28.02 over 1 gram.
Nope.
1 mole over.
Yep. I'm going to go with 1 mole of N2 over 28.02 grams N2. 1 mole N2. Any questions about that? That's the molar mass. I'll put MM over this. I am recording this too, so. Like you need one more recording to listen to, right? Yeah. That's the molar mass of N2. So that brings us to moles, and we're going to use stoichiometric ratio. So what does that look like?
3 to 2.
Let's see. I have to always check. Sometimes what I do is I put my units down, and then I go up and look at the stoichiometric coefficients. So I'm going to put mole of N2 down here, and I'm going to put mole of the NaN3 up here. So what goes here, these two?
2 to 3.
Yep, I'm liking 2 to 3. Everybody see where those came from? The 2 and the 3. 2 came from here. 3 came from here. Whoosh! I go get a cup of coffee. Okay, so my grams of N2 cancel, my moles of N2 cancel. We have moles of NaN3. So now how are we going to get to grams of NaN3? Molar mass. It's going to be that 65.02. Are we going to use it like that, or are we going to flip it? Use it like that, because we want moles to cancel. They're already in the bottom. Yep. 65.02 grams in 1 mole. Oops, sorry, grams of NaN3 mole. NaN3. All right, how should we round it? 4. Yep, I'm liking 4. Let's see what we get. Sometimes I do these twice because I'm like, if I don't get this, if I get the same answer, I'm done. If I don't, like, I must have made a mistake. But I don't have to do them twice because you guys are doing them at least once. 4 sig figs? Wow. Did you get 19.54? Cool, me too. And what would the units be? Yep. Grams of NaN3. QED. All right. So here, if it's okay with you, we're not going to go through this. I mean, I feel like we just did an extra stoichiometric calculation. So, well, let me look at it. Let you look at it, and I'll look at it and ask me if you have any questions. But as you know, these practice tests are very similar to what the real test looks like. Do you want to go around the room and take a look at it, or are we okay? How many people want to take a closer look at it? Oh, all right then. Let's do that. It's fun. I think we're doing good for time too.
Those beakers on your shoes are just nice.
They are beakers on my tennis shoes, yep. But you know, H2O, is this the one? I bought a pair of shoes that they like make it a superscript, so it says subscript. Ah. Okay, so we'll start up here, David. How about A? The term for the form of solution concentration that is defined as moles of solute per mole for a 1 liter solution.
Molarity?
Molarity. Ding, 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 ding. Okay, ready. The relationship between the amounts of reactants and products in a chemical reaction. Starts with S. Balanced equation. Stoichiometry. Stoichiometry. The stoic. Okay, Laura. The substances that are shown on the right side of the reaction arrow. Left to right. I'm liking it. Products, she says. Ding, ding, ding. Yep. Autumn. The term used to describe the physical phase of a solute that is dissolved in water. There's letter A. Yep.
Aqueous.
Aqueous. Yes. Okay. Yes. The ratio of the actual amount of product recovered relative to theoretical amounts. Do you guys remember the lab that you did last week? See, the ratio of the actual amount of product recovered relative to the theoretical amount.
No idea.
I think you're after percent yield, or I'm after percent yield there. Percent yield. Okay.
Because we had to find that at the end.
Percent yield, yeah, that was at the end. And that was that ratio of what you got back versus what you thought you get back. Okay, the error that results solely from the ineptness of the investigator. First letter G. Dork?
Dork it up.
It sounds negative. Like, ooh. Gross.
That is gross air. Gross air. Very good.
All right. So, I'm drawing for blank of people's names. I hate that. Brittany. So, Brittany, another name for a homogeneous mixture. Start with our S. Put the two together. Yes, solution. Yeah, solution. What's the other one? First she said solve it and solve you put it together and you get the solution. Very good. All right. Let's see. This is a good one, Philip. We represent 4 reasons why you can't get 100% of product. Yeah, you guys must have covered this already. So, and they're listed there. Can you explain what's meant by reaction kinetics? Do you remember?
Pathways of chemical reaction.
Yep. He said deals with the rates of, or the pathways of, various pathways of chemical reactions. Reaction kinetics, it's too darn slow. The reaction's too slow. Let's see. Again, I've got, so you are Brooklyn. I must have a problem with B's. Brooklyn. So do you remember what chemical equilibrium was? No. Chemical equilibrium was the two-way arrow, where chemical equilibrium means some goes, you know, we expect it to go to form products, but actually some products goes back to form reactants. So, okay, David, do you remember side or parallel competing reactions?
No.
Okay, so for instance, that means that like your magnesium reaction, you wanted it to form MgO, but some of it actually went and formed MgN, okay, magnesium nitride. Physical losses. What do you think about physical losses, Riley? Okay, so physical losses would be, sometimes you just can't help it. Today, oh my gosh, today you're going to have physical losses because you're going to have to kind of drain it, and you're going to lose product in the experiment. So you're physically going to lose it. Laura, for number 3, what are the products?
ALCL3
Mm-hmm.
and H2O.
I'm liking it. ALCL3, and you could have just said H2O. Yep. What are the reactants? Yeah, aluminum hydroxide. So you can write aluminum hydroxide or just Al quantity OH3. Very good. So what is the physical phase of the Al quantity OH3? Solid. It is a solid. She saw the S there. Cool. Elena, what is the stoichiometric coefficient of the AlCl3? She said 1. I'm liking it. Perfect. Ding, ding, ding. Let's see. How do we want to do this? Should you want me to do a couple balancing up there? How many people want a couple balancing? How many people are okay with it? Okay. All right. Awesome. Now number 4 is doesn't that look like what we just did? Number 4. Where would you put the question mark for number 4?
Underneath the O2.
I would put it underneath the O2. And so let's just diagram it. What would you go from left to right start with? Yep. I would start with the mass of aluminum, and then I would go to moles of aluminum using what? Molar mass of aluminum. Yep. And I would go from the moles of aluminum to moles of O2 using what? Stoichiometric ratio. Yep. And then I would go from the moles of O2 to mass of O2 using its molar mass. Are we good with that? To me, number 4 and 5 are similar. 5 is also just another stoichiometric calculation. Let's look at 6. We won't like come to the end answer, but I can't find a marker. It's driving me nuts. But I kind of feel like number 6 we did also, didn't we? Number 6, does it look familiar? Where we have the grams of the salt and we have the volume of the salt. And so how are we going to get from grams to moles? Molar mass, yep. And we also have to do a term to convert from milliliters to liters. And I feel like we did like number 7 too. I don't mean to cop out on you, but I think we just did that one. All right, number 8. I think I'll take just a minute to do number 8. Is that okay? Number 8 is the lecture that is due the 8th. Okay, so I want to show you how it's really not that bad. The balanced equation you have to be given. So we have 1 mole of NaCO3 reacting with 2 moles of HCl to form 2 moles of NaCl. 1 mole of CO2 and 1 mole of H2O. So notice in the description they give you some information. And in my videos what you're going to hear is that I like to take this information, kind of like stoichiometric calculations, and put it under the thing it's talking about. So it says how many milliliters of 0.115 molar Na2CO3. So what I'll be looking for when you guys work this, what I'll be looking for you guys is to find Na2CO3. I'm going to write question mark milliliters, and then I'm going to write the 0.115 big M. I'm just lining it up under my NaCO3. Then it goes ahead, is required to blah, 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 to react with 50 milliliters of 0.323 molar HCl. So that volume and the molarity goes with HCl. So I'll find my HCl and I'm going to write 50.0 milliliters under my HCl and 0.323 big M under my HCl. So I feel organized. I feel empowered. So what you're going to hear on this is called, it deals with solutions, because there's NaCO3 and HCl are both aqueous solutions, and it deals with stoichiometry, so it's solution stoichiometric calculations. I'm always going to tell you to start with what you know most about, which is the HCl. So step number 1 is we're going to use volume and molarity to get to moles of HCl from, I'll just put big V, volume, and big M. We good with that? Moles of HCl. Once we have moles of HCl, this will sound familiar to you, I think. We can now get to moles of the other thing, which is NaCO3 from stoichiometry. And then once we have moles of NaCO3, the last step in this case is we can, I'm just going to say use moles and molarity. I'll put a big M for molarity to get to the volume of NaCO3. You're going to probably hear in my videos where I'm all about labeling things and just kind of showing how you're working the problem. But this last problem that you're going to cover next week in your lecture video, you can do it. It's really very doable. Do you want to see me work this, or are you okay with this? Okay. Very good. step number 1. Okay, so my first step was to look at this for HCl and to get to moles. So what I like to do is I like to put the volume over 1. So I'm going to put 50.0, oh, actually, I'm going to label this. I'm going to say moles of HCl. And the reason I label it is because then I don't have to write HCl, HCl, HCl. So I'm going to title this number 1, moles of HCl. So at 50.0 milliliters solution, I'm going to put that over 1. I could ask you to unpack this 0.323 big M, and you would tell me it's 0.323 moles of HCl per 1 liter solution, right? So I'm going to use this to my advantage, but of course I need to get this to liters first. So how do I get this to liters?
Or 1 liter over 1,000.
Yep, 1 liter solution over 1,000 milliliters. Perfect. Now what can I do to get to moles? Yep, now I can just bring this molarity over. 0.323 moles over 1 liter of solution. Now, as long as I have titled my thing, I don't have to say of HCl and all that. How many sig figs? 3. So dyslexic there. I got 0.0162. Oops. And units would be moles. I'll go ahead and slap the HCl on there. So I did this. I got my moles of HCl. Now I'm going to go ahead and get to my moles of NaCO3 using a similar thing to what we did the other stoichiometric calculations. So for my next one, I'm going to take this as my first term. So my first term is going to be 0.0162 moles of HCl over 1. And this is kind of like what I said before. I like to put this is my stoic ratio, and I like to put the units, moles HCl on the bottom, moles of NaCO3 on the top, and then I go back and so what are the numbers? From the balanced
That
equation.
would be 0.115.
So these are going to be the stoichiometric coefficients. Yeah, that's fine. What do you think? 1 over 2? I'm liking it. So if I have this in my calculator, all I gotta do is divide by 2. I got 0.00808. And in this case, my units now are moles of NaCO3. Cool. Now we're ready for the third step. And kind of like what we did with the second step, I'm going to use this as a starting point. So, oh, is it Na2? It's not, sorry. Okay. So, my third step, I'm going to use that as a starting point, 0.00808 moles of Na2CO3. I'm going to put that over 1. So if I were gonna unpack this, 0.115, what does that mean? CO3, 1 liter solution, right? So how can I use this to get to liters of solution? Do I leave it like that or do I flip it? I flip it. Flip it good. Yep. So 1 liter solution over 0.115 moles of Na2CO3. Whoosh! 3 sig figs. I get 0.0702. What would the units be? So that would give us liters. We could take it all the way to milliliters. Did it ask for milliliters?
Yeah.
Oh. So how are we going to do that last step? Yep. I'm liking 1,000 milliliters over 1 liter. So that gives me what, 70.2? Now that would be milliliters of your solution. All right. Whoosh. Cool. All right, so let's kind of get her moving and we'll meet in the lab.